Hello everyone, welcome to my section. My name is Xuanan Shu. I'm a software engineer at Alibaba. Today we're going to talk about a project that helps running TensorFlow application on Apache Flink. Here's the agenda of today's talk. We will first talk about the background and the motivation of the project. We will then have a look at how we combine TensorFlow and Flink to run the TensorFlow machine learning cluster on Apache Flink. After we have the TensorFlow running on Flink, we want to generalize the idea and provide an abstraction to run any kinds of machine learning cluster on Flink. At the end, we will quickly summarize and talk about some of the future work. Without further ado, let's talk about the background and motivation of the project. Before we begin, since we are going to talk about a project that combines TensorFlow and Apache Flink, I will give you a little bit background of TensorFlow. For Flink, since this is a Flink forward, I'm assuming everyone should already familiar with it. So TensorFlow is an open source project that it has a comprehensive library and tools for machine learning. It is one of the most popular AI computing framework. Its comprehensive library lets developer and data scientists easily build and train a machine learning model. Now, we are going to have a look at a typical machine learning workflow. It uses Flink and TensorFlow separately. At the beginning, we have the feature engineering. It consumes unstructured raw data and apply a sequence of transformation to data. At the end, it should produce some well-structured and read data that are ready to be used to train a machine learning model. This step is all about data processing, and it is what Apache Flink is good for. Therefore, it is done with Flink. After we have the well-structured data, we need to train a machine learning model. This part is typically done with the help of TensorFlow. TensorFlow provides the rich library to help developers to build and train a machine learning model easily. And after the training, the trained model can be used for offline inference or nearline inference. Here we are talking about latency above a second. And if you're looking for low latency online inference with latency at milliseconds, you may want to use TensorFlow serving. Both of them will produce some prediction results that can be used for other services. Here, the machine learning workflow can work, but it also have some shortcomings. As we can see, one simple machine learning project can have multiple steps. We have feature engineering, model training, and inference. And we need to use both Flink and TensorFlow to complete the work. This introduces complexity to deploy and maintain two different systems. And since there are two different frameworks, if you have your feature engineering and pre-processing done in Flink, then you will have to write the data out to some kind of external storage so that TensorFlow can use that data to do model training or inference. In addition, deploy a machine learning cluster with TensorFlow to run model training in distributed manner is not an easy task. For example, it requires you to determine the IP and port of the machine that are going to run the TensorFlow code. However, in production, it is not always possible to have that information upfront. In a young cluster, you cannot determine the IP and port until the job is scheduled. And when you run TensorFlow or any kind of application in distributed manner, it is very important to have some kind of failure recovery to handle the failure automatically. But TensorFlow doesn't have that out of the box. And here is what we want to run a machine learning cluster workflow ideally. We want to have all the work to be done in only one single system so that we don't have to deal with the complexity of two systems. And we don't want to write the pre-processed data to any external system just because TensorFlow cannot consume the intermediate result in Flink. And we don't want to deploy and manage the machine learning cluster. We want to dynamically deploy a machine learning cluster on demand and have all the information about the cluster available when running the machine learning application. And we want the machine learning cluster to have the capability to recover from failure automatically. In order to solve the problem, we came up with an idea. Why not run TensorFlow on Flink? Why not utilize the failure recovery mechanism provided in Flink, and so that we can abstract away the complexity to run TensorFlow machine learning cluster. And here is our solution, TensorFlow on Flink. We will explain how we managed to run TensorFlow on Flink and solve the given problems. First of all, let's have a look at the architecture of a machine learning cluster that used to run a TensorFlow application in distributed manner. In this setup, some nodes are designated as worker, while others are designated as parameter server, which is shown as the PS node in the graph. And the worker node are the node that do the actual computation of the machine learning algorithm. They are independently chaining over some input data, and they will periodically send message to the parameter server to update the parameter. This architecture is commonly used when the machine learning model is too large to load into a single machine. And we aim to help writing such distributed machine learning application easily and run on Flink. And before we dive deep, I want to quickly review the topology of a Flink program. This is a logical view of a Flink program. It consists of different operators. In this example, we have source, join, flat map, and sync. At runtime, Flink will run each operator in parallel in task managers. Each operator has a property called parallelism that controls how many instances of that operator should run in parallel at runtime. Now that we have reviewed the topology of a Flink job, and we have seen the architecture of a machine learning cluster or a TensorFlow cluster, we can now talk about how we are going to combine the operator in Flink job with the component of the TensorFlow cluster. We will start from a single worker. In order to run the worker in Flink, we can wrap the Flink operator. We can wrap it in a Flink operator so that the Flink runtime will assign the task manager to run that worker as an operator. Now, what if I want to have 3 workers in my TensorFlow cluster? And that can be achieved by setting the parallelism of the operator. In this case, we set the parallelism of the operator to 3. And Flink runtime will submit 3 tasks to TM to run the operator in parallel. And the whole idea is exactly the same for the parameter server. And it has the parallelism set to 2. And to manage the status and the life cycle of all these nodes, as well as the machine learning cluster, we also need to have an application manager. And it will run in a Flink operator as well. Based on this idea, we can run TensorFlow application as operator on Flink. In the next couple of slides, I will go through different scenarios that will leverage this idea to run TensorFlow on Flink. Here's the first case we will look at. This is the case when you have your training data ready, and it is called the sample files in the picture. We call this case batch training. In this case, you can use TensorFlow operator provided in TensorFlow to read the data directly. The sample file is typically stored in some kind of distributed file system and can be accessed by the worker in the cluster. And Flink will run the worker and parameter server in the Flink source operator. And the parallelism of the source operator will corresponding to the number of worker or parameter node set by the user. The application manager always runs in source operator with parallelism of 1. While the model is training, the worker need to fetch the parameter from the parameter server and then update the parameter. And such communication you will use the gRPC provided in TensorFlow. Similar to batch training, we also have batch inference. Each input data is also stored in some distributed file system. The only difference is that we need to give the trained model at the beginning for inference. Next, we have the stream training. This is the case when you do not have the preprocessed data ready and you want to leverage the power of Flink to do the preprocessing or feature engineering from the raw data. As in the picture, you may have two sources that read from some raw data, followed by a joint operator, and apply some UDTF to transform the record to a format that can be understood by TensorFlow. That data will then send to the machine learning cluster for model training. In such case, we need to consume the intermediate result in Flink. Therefore, the workers are running in a flat map operator when you are using DataStream API, or it will run in a UDTF when you are using the table or SQL API. The parameter server and the application manager, on the other hand, will run in the source operator since they do not need to consume any data. As you may have known, the TensorFlow application is commonly written in Python and running in a Python process, while Flink application is running in a Java process. This puts a challenge on how to exchange the data between Python process and the Flink process, the Java process. And here's how we do the inter-process communication. We implement a memory queue that uses shared memory. The Java object will first get encoded and put into a memory queue. The Python process will then read the data from the memory queue, decode the data to a Python object that can be understood and used by the TensorFlow. And sending the data from Python process to Java process is the reverse, and it uses the same memory queue implementation. The memory queue only introduced 10% of performance overhead compared to running the same logic without memory queue in a Java process. And you may have noticed that you need to have encoder and decoder in both Java and Python process. And we provide a handful of encoder and decoder for some commonly used objects. For example, we have encoder and decoder for the row object in Flink, JSON object, byte array, etc. For others, you can always implement your own encoder and decoders. After chaining, after we have the chained model, now we need to do inference. As you can see, the machine learning cluster will have the same architecture as training. Therefore, the stream inference pretty much run the same way on Flink as the stream training. The pre-processing pipeline is the same, and we can reuse the code. The only difference is that model is given at the beginning of the inference. The parameter server will load the parameter of the model, and the worker will read the data from the upstream operator, perform an inference, and send the result to the downstream operator. The machine learning cluster that includes both parameter server and workers are only required if your machine learning model is too large to store in a single machine. And such scenario is commonly seen in search ranking and recommending system. But when the chained model can be loaded into a single machine, we can get rid of the PS, the parameter server, and the whole machine learning cluster look like this. Here we have the same pre-processing pipeline, and we only have worker running in flat map operator or UTF without a parameter server. The worker will load the model and the parameter and perform the inference using the TensorFlow Java API. Therefore, the worker is running as a Java process. In this case, we don't need to have the inter-process communication between Python and Java. And as a user, you only need to provide the model and specify how many workers you need. The inference result will send to the downstream operator. And when you run a application, TensorFlow application in distributed manner, it is very likely that some failure can happen. And here we are going to talk about how these failures are handled. The first case we will see is that the failure on the task manager. In this case, it will be treated as a normal TM fails, and the Flink will handle such failure automatically by restarting the Flink job. And what happens if a machine learning node fails? For example, the Python process that runs the machine learning script fails. In this case, the heartbeat from the failing node to application manager will time out, and the application manager will notice that there's a failing node in the cluster, and it will send a message to all the machine learning nodes to notify them and restart the machine learning node. Now, how about the application manager fails? In this case, since the application manager is running as an operator in Flink, Flink will treat it as a job failing and restart the job automatically. And this is how TensorFlow on Flink provide the failure recovery. Let's step back and look at the machine learning workflow we introduced at the beginning. With all the things we have done to run TensorFlow on Flink, now we can replace the TensorFlow, and we can have the model training and inference run in Flink. So that now we only need one system to complete the machine learning workflow. Okay, now we can run TensorFlow on Flink, and let's call it a day. But is that all? What if I want to run PyTorch on Flink? And here we need to have a general solution for all kinds of machine learning cluster. And here we are, the generalized TensorFlow on Flink. We call it Flink AI Extended. Again, let's start from the worker PS architecture that used to distributed train a machine learning model with TensorFlow. We have some number of workers and a couple of parameter server in the cluster. So how can we generalize such cluster so that it can be used for other setup of machine learning cluster? We noticed that both worker and parameter server are just nodes that execute some machine learning code. Therefore, they are all nodes just with different roles. And they are assigned to different groups based on their roles. Their role. In this case, we have 3 nodes that with worker role and 2 nodes with PS role, the parameter server roles. And we always have a application manager that manages the status of the nodes and the life cycle of the cluster. And this is the core abstraction that Flink AI Extended provides. And here's the structure of the Flink AI Extended project. At the very bottom layer, we have the ML framework along with the Flink runtime. The ML framework is an abstraction over the machine learning cluster. It is responsible for create and managing the machine learning cluster. It implements the communication, the service discovery, and the node state management of the machine learning cluster. And in the middle layer, we have the ML operator. The ML operator combines the underlying Flink runtime with the ML framework. You can look at it as a library to create a machine learning cluster as a Flink job. In other words, it exposes the concept of nodes and application manager to the user, and it also runs the machine learning cluster and run in Flink runtime. On top of the ML operator, we have different implementation for different machine learning library. For now, we support TensorFlow and PyTorch. In the next couple of slides, I will go through the ML framework and the ML operator module. Let's have a deeper look at the ML framework. The ML framework have 2 important components, namely the application manager and the nodes. Application manager will records the status of the nodes and manage their life cycle. It will accept registration and monitor the heartbeats from the nodes. As you can see, Application Manager has a state machine inside. It uses state machine to handle the status change from the nodes and update the status of the cluster. For example, an AM can restart all the machine learning node when it finds out that there is a failing node. And we make the state machine extensible so that different machine learning clusters can customize their own state machine to better fit their needs. The node, on the other hand, is responsible for running the actual machine learning algorithm. The node is responsible for setting up the running environment. For example, you need to have Python and TensorFlow in the environment in order to run the TensorFlow application. And in every node, we see there is a abstract runner inside. And it is responsible for running the actual startup process and running the actual machine learning script. Different machine learning frameworks can have their own implementation of the runner so that we can support running different running script from different machine learning framework. Now that we have provided a machine learning cluster abstraction in the ML framework, how can we expose those concepts to user and run TensorFlow and run machine learning cluster on Flink? And that leads to the ML operator. The ML operator provides two important methods, add AM row and add row. The add AM row should be called once for every machine learning application. It will add a Flink operator to a Flink job, and the operator has the application manager running inside. And this is the application manager in the ML framework. The add row will add a group of nodes to the machine learning cluster, and it does it by adding a Flink operator to the Flink job, and the nodes runs in the Flink operator. It also controls the number of nodes by setting the parallelism of the operator. Similar to running TensorFlow on Flink, we have two different cases depending on whether the machine learning application consumes the data directly with the machine learning library, or it consumes the data from upstream operator in a Flink job. So when the machine learning application is responsible for reading the input data from external system, it is called a batch mode. For example, it could read the data that are stored in a distributed file system. In this case, Flink does not need to handle the I/O for machine learning application, and all it should be doing is spawning the application manager and the right number of nodes. Therefore, we use Flink source operator to run both application manager and the nodes. When the machine learning cluster, the machine learning application need to consume data produced by some upstream operator in Flink. This is the case when feature engineering is done by some upstream operator in Flink, and the machine learning application want to consume that data without writing it out to an external system, and we name such case stream mode. As we can see from the graph, since we need to consume data that produced by some upstream operator, the node is running as a flat map operator. For simplicity, the graph only shows the upstream operator as a source operator. In reality, this could be a complex feature engineering pipeline. And another thing to point out is that since the application manager doesn't need to consume any data, it's always running in a source the Flink source operator. And the inter-process communication between the Java process and the Python process use the same implementation of memory queue when running TensorFlow on Flink. Now we can run all kinds of machine learning cluster with the abstraction provided by Flink AI Extended. Last but not least, I will give a short summary and talk about some of the future work. To summarize today's talk, we start with the shortcomings of running a machine learning workflow with Flink and TensorFlow separately. And to solve the problem, we introduce how to run TensorFlow as an operator on Flink, so that we only have to deal with one framework. We don't have to write the data out in, that process in Flink to an external storage. We don't have to manage the machine learning cluster ourselves, and it has fault tolerance out of the box. After that, we then generalize the idea and introduce the project called Flink AI Extended, so that different machine learning cluster can run as operator on Flink and enjoy all the benefits. Next, I will talk about some ongoing efforts of the project. So the ML framework in the Flink AI Extended provides an abstraction to create and manage a machine learning cluster. We believe that such abstraction can enrich the machine learning ecosystem of Flink. And in Flink 1.11, we also introduced the operator coordinator to handle the communication between operators. And so it becomes more natural to run the application manager in the operator coordinator. Therefore, we decide to contribute the abstraction of machine learning cluster to Flink. And as you may have noticed, to run a TensorFlow on Flink, currently you need to write a machine learning application in Python and write a Flink job in Java. This is not convenient and user-friendly to switch between two languages. Therefore, some effort has been put into integrating with PyFlink. If you are not familiar with PyFlink, it basically allows you to write a Flink program in Python. And some of the work in Flink AI Extended aligns with the work have done in PyFlink project. For example, when a TensorFlow application runs on Flink, it requires a Python environment in order to execute the machine learning script. And PyFlink have a way to set up the Python environment in Flink project. And the inter-process communication between Flink process and machine learning process is also implemented in PyFlink. Last but not least, in Flip 36, we introduced a caching mechanism to cache the intermediate result using Table API. This is very helpful when you want to hyperparameter tuning. The intermediate result can be cached and used by multiple model training jobs. On top of that, it will allow machine learning application running on Flink to consume the same intermediate result multiple times to do iterative model training. With that, it ends my presentation, and thanks for your attention.